All right, let's take a look at our website here. Our website, web access site, is now going to start to be populated with notes. And each of these weeks that we have 2 lectures a week. Each of these weeks will have class notes that you can download or you can view online. So these are the exact same notes that I took during the last class. Okay, so it's all there available for you if you want. I normally would open up a new window for this, but I forgot to do that here, and so I need to adjust that. Today I'm actually recording the lectures, and I'll record the lectures from now on. So there'll be YouTube videos of the lectures that you can also view at some point. Okay. So last time we started to talk about vectors, and there's some properties of vectors that are might seem obvious, and we'll discuss them and we'll list them down. And then we're going to go ahead and start talking about the dot product, and then get a start on discussing lines and planes. We know a lot about lines, but we're going to take a look at lines from a slightly different point of view, and then we'll also extend our ideas to talk about planes. So if you've taken Calc 3, you have an advantage. I was going to say a little advantage, but it might be a big advantage depending on how much you remember. Well, depending on how much you remember, it might be a little advantage. But you'll have some advantage in discussing planes, because in Calc 3 is when we start taking a look at 3-dimensional objects. And so actually a plane is a 2-dimensional object in 3 dimensions. So we'll talk about what those dimensions mean and how they play a part in linear algebra. All right, that is our plan. Let's see where we can go with this. All right, I think last time we talked about vectors, we talked about scalar multiplication. So let's carry on and move to vectors that are beyond our visual abilities. And so those would be vectors that are in R4, 5, 6, R whatever. And really, you can make it as many dimensions as you want. You can define a vector as many dimensions as you want. And so here is, oh, I forgot to start up my other. I have to get used to this again. So there's a few things I need to start up before I start the class. The recorder, I need the browser, I need my notes, and I need this thing, which is my little blackboard. So vectors in Rn, where n is some number that actually can stand for 1. It could be 1, 2, 3. If it was an R1, then that would just be the set of real numbers, and that's not a big deal. If it's an R2, then it's the xy plane. Why don't I write that down instead of just saying it? R1 would just be real numbers. And you could actually denote this geometrically with just a number line. You can even anchor it at 0 if you want to, but it's just a number line that has real numbers. So this is a, I'll say it now, we'll talk about it later on. It's a 1-dimension. R2 is going to be our Cartesian plane. And we can view that geometrically with our xy plane. Although xy are dummy variables, we can label it uv, or you can label it whatever you want. Sometimes in physics, when we talk about something with respect to time, the x-axis is a t-axis instead of an x, and then the y could be position or velocity or whatever. And it would make sense for us to look at this as something that's two-dimensional. And then when we talk about R3, this is going to be our 3D space. And like I said, if you've taken Calc 3 before, then you might be familiar drawing a three-dimensional space with usually denoted by x, y, and z, but can be denoted with whatever variables we want. And this is 3 dimensions. So it's pretty clear that when we talk about Rn, then n would be your n dimensions. Okay, so when we talk about Rn, we're saying it's a vector that has that many components. So for a real number, an example for this would just be numbers. I don't know, 2 seems like a good example. It's just a number. An example for something in the Cartesian plane would be an ordered pair, like 1, 1. And an example in 3 dimensions would be like 1, 1, 1. I don't know if you can visualize that, but that's how we would try to draw this thing in 3 dimensions. So it would have 3 components. Now, notice I was drawing points, but I think I was trying to make it clear last time that when we see a point, it can be a vector, and that vector would be a vector in standard position. So we can imagine our vector with the tail at the origin and then the head pointing at whatever it's pointing. So our simple one-dimensional vector is going to be a vector from 0, an arrow from 0 to 2. Our vector over here would be a 2-dimensional vector from 0 to 1, 1, 1. And then this one is hard to visualize, but imagine going from 0 to this. Okay, so that's as far as we can see, as far as we can visualize, because our eyes can only visualize 3 dimensions. So beyond that, we can't visualize it anymore, so we have to just abstractly talk about something in R4, for example. So this is you looking at something. This is your eye. Does it look like an eye? Now does it look like an eye? So you can't visualize it, but you can certainly come up with examples. That's the easy part. So a vector in R4 can be something that looks like 1, 0, 0, 1, for example. So that can be a point in 4 dimensions, but you can't see it. Well, you just have to trust that it's a point in 4 dimensions. Or you can take a look at it as if it was a vector in 4 dimensions. Okay? The example that I always like to show people is your grade vector. What? So according to your grade, your grade is going to be based on the homework, quiz, let's see, homework, quiz, worksheets, exams, the final exam, and STEM speaker series. So for me, I would create a 6-dimensional grade vector for each of you. So each of you would have a 6-dimensional grade vector. What does that mean? In R6, we have a 6-dimensional grade vector. And what this would be, this would be a collection of percentages of each of the categories that we have. So your vector will be composed of your homework, your quizzes, your exams, your final exam, STEM speaker series. I said 6, right? Worksheets. And how I set this up is important. This is an ordered, I was going to say pair, an ordered 6-tuple. Have you guys heard of tuple? When you have a scalar, that's just a single. If you have a Cartesian plane in R2, you say a double or a pair. And when you have something in R3, you would say triple. But when you have something higher than that, you say tuple, n-tuple. So a 4-tuple, a 5-tuple, a 6-tuple. And what's important here is that it has to be ordered. So I don't know if when I do your grades, I don't put it in this order. I put the final exam last usually. That's like my last component. But let's just write it like this because that's how I wrote it already. So each person will get a grade vector. Let's take Maria here. And I'll call my vector MT for Maria. And let's see, what did she get in her homework? 40%. And what are her quiz averages? 80%. She got a 10 on the first quiz. What's her exam average? There's 2 exams, I average it out. What's her exam average? 75%. And her final exam, she took the final, what? 100. Wow. She went to all the STEM speaker series. And did she do her worksheets? What did she get in her worksheets? She didn't do any worksheets. So this is the grade vector for Maria. It's a 6-dimensional vector that describes her grade for the class. Now, it doesn't describe her overall grade, and we'll need to do something else to figure out her overall grade, but this, for now, is her grade vector. Okay? And there are many other examples. You guys are familiar with binary code. Are you guys familiar with binary code? We'll eventually discuss binary numbers and numbers of base 5 or something different aside from base 10, because they provide interesting applications. But let me just throw in one more example here of, I guess, in computer science, they discuss things in binary, but they also go to, have you heard of hexadecimal? What's the base for hexadecimal? 16. So for hexadecimal, it's base 16. And so if I were to describe something in hexadecimal, I have zeros and ones. And for this, I would probably write it as a row vector instead of a vector with commas in between. I would write it as a row vector because I'm just dealing with zeros and ones, and so I can distinguish between 1 and 0 versus 10. So I could just write this a vector with no commas. And then you would have 16 digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You would have a digit that looks like, you'd have a vector that looks like this, and a computer would look at this and say, okay, that is actually number Anybody? Anybody? Takes a minute, but yeah, I guess if you formally go hexadecimal, but I want to look at hexadecimal from a binary point of view. So it's a 16-digit binary number, and this gets translated, and this is actually a number. If you're able to figure it out before the end of class, I'll give you a little mini chocolate bar next time. All right, here's how you do it. This is 1, 2, 4, 1, 2, 4, 8, 16. I lost count. So this is 1 and no contributions. And what did I say? This is 4. This is 8. No contribution, no contribution. Okay. All right, that's my hint for non-computer science people if you want a shot at the chocolate. Okay. So that's the basic idea with n-dimensional vectors. And these n-dimensional vectors work the same way as these other vectors that we looked at yesterday, the R2 and R3 vectors, because when you add them component-wise. Now, we get a visual for R2 and R3 because you know that parallelogram that we drew last time, but in R4 or higher, you can't visualize it. But the computation is just as easy. It's the same way. So when we talk about adding them, oops. Here, let me start up another page about adding them. So when you're adding vectors, for example, why would we add vectors? I don't know. Let's go back to zeros. Let's just have a simple example in R5. So let's say V was equal to 1, 2, 3, 4, 5, and U was equal to 7, 4, 0, -1, 2. And so it's clear, it should be clear when we're adding two vectors, we end up with another vector. Our vectors that we would add would be just adding component-wise. So I would just add 1 and 7, that's 8, and then this is 6, this is 3, this is 3, and 7. So that's going to be my new vector. So subtraction would also work. Did I add correctly? I have problems adding sometimes. Is that right? Okay. You can subtract. So V minus U, 1 minus 7 is -6. This is -2. This is 3. This is +5. And this is 3. So you can also subtract. You can also scalar multiply. Those are our third. That's our third operation that we've discussed so far, right? Just adding, subtracting, and scalar multiplying. So I take 5V. I would take 5 and multiply every component in V by 5. So that would just be 5, 10, 15, 20, and 25. So the idea is that I can do this in any dimension. The only thing is that if you're going to add or subtract vectors, you want to make sure that you're in the same dimension because you're not going to be able to add something in a different dimension unless you have pre-set restrictions like if the dimension's not there, then you just assume it's equal to 0 or something. All right, so these are some of the basic operations that we've discussed already, and these basic operations have certain properties like commutativity and associativity. So I would just like to list down those properties and not really talk much about them. In a more mathematical linear algebra class, we would spend time proving this. I think it would be good to prove one or two of these sometime, but I don't feel like doing it now, so we'll just leave it like that. Okay? And these are mainly used in proving more complicated theorems and ideas, but these are essentially properties that can be easily proved. Oh, let's prove one. Let's see, which one's an easy one to prove? Number 3 is really easy. So, to formally prove this in Rn, because here you're assuming you're in Rn, to formally prove this, what you have to do is, for these ones, the ones establishing properties are fairly simple. What we're going to do is we're going to assume that U is a vector in Rn, which means I have to write U as a vector with n components, whatever n is. And so to do that, and the components could be any number, to do that, we're going to assume that U is equal to some number, and we'll just call it U1, another number, and we'll call it U2, and then I need n of them, so the way mathematicians usually deal with that is they just put dot, 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 and then they put U sub n. So this would say that there are n numbers from 1 to n. Of course, if you're in computer science, you would start from 0 to n minus 1, which gets a little confusing sometimes. But I have an n-dimensional vector in U, and the 0, and now look at the 0, it has a little arrow on top, so I know that's a 0 vector, not the 0 scalar. So a 0 vector is going to look like this, where there's n of them, and then U plus 0, the 0 vector, is going to be adding this component-wise. Now, this is where it gets a little tedious, but it has to be written down if you're formally proving it. So as a mathematician, I'm formally proving this. The definition of addition means I have to add component by component. So I would add U1 plus 0. That's the first component. I would add U2 plus 0. That's the second component. And then I would do the same thing for all the other components, including the last one, which is U sub n plus 0. And then from here, it becomes our usual math and our usual arithmetic, that the arithmetic we learned in kindergarten or whatever we learned arithmetic. You would add a number plus 0 is, we know that that's just a number. So this is un, or U1, U2, dot, 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 un, and that happens to be equal to U, the original vector U. And so the string of equalities from here to here to here to here ends our proof. That's a string of inequalities. So the work that we did goes between these two sides, and then we got from the left side to the right side, and so we're done with the proof. So we usually end the proof with some symbol, or in books they sometimes put a little box or something like that, or a double slash, but mathematicians use QED. What's QED? Kid. Mathematicians got used to doing that. It's quod eras demonstratum, which is Latin for that which was to be proved. Anybody speak Latin? Yeah. So it's a Latin phrase that a lot of people have used in the past to say that this is what they're proving. Okay. Yeah, if you're going to be a math major, you're going to get used to that QED business. So that's the story for proving things, and I'll prove one. The book has proofs of some. The book proves the first property and second property, so you can take a look at the process of proving things mathematically. I may ask you something like this on the exam, just for fun. Okay. And then in terms of the adding and scalar multiplying, subtracting is like adding a scalar multiple of a negative of another vector. So it's kind of like the same thing. But in light of all this adding and scalar multiplying, we have what's called a linear combination. And this phrase will become very, very, very important for us in this class. And they do this for, they call it, I guess they went to k this time. No, that's just a k vector. N can be in any dimensions. But if you have a set of vectors, v1 through vk, a linear combination just means you're going to scale v1 and add it to a scale of v2 and add it to a scale of v3, etc. So it's basically scalar multiplication and addition combined and adding up all those vectors. So, for example, if we have v1, let's go 2 dimensions on this just to make it easy for us. v1 is, let me change it up too, just to confuse you. I mean, to get you used to different notation. I'm going to use a row vector this time. So a linear combination of this would just mean that I would multiply this by a number and then add the vector v1. And right now I'm putting a blank space here. And then another number plus v2, and then another number plus v3. So what those numbers are, C1, C2, C3, those are the coefficients of these vectors, and I can have a coefficient list. So I can write, I suppose I can just arbitrarily choose numbers here, 2, 3, and -1, for example. Then this is a linear combination. -1 looks a little... And so we can just work this out, I suppose. This is 410 plus 30 plus +1, -2. And if you remember, you're adding things. I have 3 things that I'm adding, so we can just add across. 4, 3, and 1 is 8. And 10, -2 is 8. So I have 8, 8. So W, the vector W, is going to equal 8, 8. And that is a linear combination of V1, V2, and V3. Yeah?
You just chose those coefficients
arbitrarily, randomly. The more interesting approach to studying linear combinations is usually you're given a vector and you would write the linear combination saying 8, 8 is a linear combination of V1, V2, and V3. And the question would be, what should these coefficients be? That's the more interesting question, and that's we're not going to answer that today. Well, actually, we can answer this one because we made it up, right? We made up this problem, so we know what the answer is. But later on, that's going to be the question that we're going to be asking about linear combinations, is that can we represent this vector 8, 8 as a linear combination of these three vectors? And if we can, we should be able to find these numbers. We'll call them C1, C2, and C3, so that when you put them as a linear combination with C1, C2, C3 as coefficients, then I'm going to get the vector that I wanted in the first place. Okay? So that's going to be a more common problem for us and that's one use of the idea of a linear combination. Okay? Questions? Yeah. B equals NP? I don't know. I'm not familiar with that. Maybe I should look it up. But I'll try to look it up. So the answer to your question is I don't know. But there probably is a relation. Yeah. Okay, any other questions?
Is the same if we put a component in parentheses in range of that form?
Yes. Like if I were to put 8, 8 equals, yeah, same thing. Yeah, this is the time when I said I'm just going to confuse you. Oh, I mean, get you used to using different things. So I want you to be flexible with using, because I like using these things with commas, but I know the textbook sometimes uses the column vectors, and we might need to use column vectors at times. So I want us to get used to the same. So yeah, they're the same thing. Okay? Oh, I guess they do answer that question already in the book, huh? All right. I'll let you guys figure that out. Before we go to the dot product, and it looks like we're going to fall behind already in our schedule. But that's expected. Before we go to the dot product, I want to talk a little bit about the different number systems that they have in the textbook, because there's a few questions and applications that use different number systems. And by number systems, I mean like binary number system, for example. So we live in a decimal number system. Oh, man. And I think that's because we have 10 fingers. So because we have 10 fingers, people decided back a long time ago that you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm done with my fingers. So we start doubling up. So 11 has 2 digits. And so the whole idea about base is what digits are you able to use? So in a base 10 number system, your digits are 0, 1, 2, through 9. And so you're allowed these 10 digits, and when you get to 9, you're out of digits, so you start combining things. So you have 1, 0 for 10, 1, 1 for 11, 1, 2 for 12, etc. So the same thing goes for the other systems, except if we didn't have 10 fingers, let's say we didn't have fingers and we just had nubs, and so we only have two things, and so that could be an impetus for having a binary system. Just use 1, 0, 1, 1, 2. So your numbers that you can use are just zeros and ones. You only have 2 digits. So that means that this is 1, or this is 0, and this is 1. And when you want to denote 2, you don't have any more digits, so you have to start combining them. So this is 2. Three, and then now you're out of digits again, so you get a 4. 5, 6, 7, now you're out of digits again, 8. So this is how you would denote these digits in binary, because you only have zeros and ones to deal with. So the advantage is that you only have two digits to deal with. That's nice and easy. The disadvantage is that the number 8 now has 4 digits, and that gets to be a lot. If you don't care too much about being able to keep track of that stuff, then this would be a good way to denote things. So, you know how in whatever first, second, third grade, when you have to expand your number, you have like 1,325, and so that's like 1 times 1,000, and then what did I say? 100, 200, 2 times 100, and remember that? So that exercise, as I don't know what you thought about that exercise, 1,235 is equal to 1 times 1,000 plus 2 times 100 plus 3 times 10 plus 5 times 1. Remember that exercise? Did you think that was pointless? That was so pointless. It's so useless. And then when we learned exponents, we found out that we can write it like this is 1 times, instead of 1,000, that's 10 to the 3rd power. And instead of 2 times 100, that's 10 to the 2nd power. And 3 times 10 to the 1st power. Plus 5 times 10 to the 0th power. You know that 1 is 10 to the 0th, right? So this is where it becomes really clear that we're on base 10, because we're using 10 powers. Well, it turns out that's the same way that goes for binary. This expression, to be able to write this as an expanded form, works in any base that we want. And in any base, we just have to change the 10 to whatever base we're dealing with. So 101, 101, this is 1 times 2, that's not 2, 2 to the, this is 0, 1, 2, this is the second power, plus 0 times 2 to the first power, plus 0 times 2 to the 0th power. So if we take a look at the digits being a factor of 2 to some power, like this, and then add it up like we did in the expanded form here, 2 times 2, or 2 squared is 4, plus 0, plus, and 2 to the 0 power. Oh, this should be a 1. That last digit is a 1. So this is 1 times 2 to the 0, which is 1. And 4 plus 1 is 5. Which is how that's denoted. So I think I just told you the secret to that candy problem. Except you'd have to go 16 digits. Okay? The other interesting thing is these tens, hundreds, and thousands, or at least they look like 10, 100, and 1,000. That's like 10 to the first, 10 to the second, 10 to the third, if you were in decimal system. But if you're in binary, this would be 2 to the first, or 2 to the 0, 2 to the first, 2 to the second, 2 to the third. And you would guess that 1, 0, 0, 0, 0 would be 2 to the fourth power, which is 16, I think. All right. So that's the binary system. But for us, we're going to stick with just zeros and ones and dealing with zeros and ones, and we're not going to expand our number system to these things. Let's just deal with zeros and ones as zeros and ones. So let's look at a more simplified binary system. Yeah, let me just say it that way. All right, I'll say it. So there's another number system that's related to the binary number system called Galois Field 2. Galois is a French mathematician. Anybody speak French? Am I pronouncing that properly? Galois? So Galois Field 2, which is a field of numbers that only has zeros and ones. Okay? What does that mean? So I didn't talk about fields yet. Field is actually a vital subject in this class, but the book and a lot of other introductory linear algebra books don't really talk about vector fields until later on. But a field is a set of numbers that's closed within addition and multiplication, which means if I multiply two numbers in that field, I'm going to get another number in that field. Now, let me just quick detour on fields. So examples of fields are the field of real numbers. So if I add two real numbers, I'm going to get another real number. If I multiply two real numbers, I'm going to get another real number. Okay. Another example of a field is a set of complex numbers. So when we're talking about things that I'm not really going to dive into, it's important to know what examples are of fields, but it might also be good to take a look at examples of things that are not fields. So an example of something that's not a field would be adding, subtracting. Let's see if this will work out. Yeah, there's more things about fields that I need to talk about, but that's going to take too much time. So some examples of things that are not fields are integers. They usually denote it with a Z. This is not a field because it has so a field has more things than I was trying to explain. So this is multiplicative inverse, M-U-L-T, multiplicative inverse. That means if I have 2, the multiplicative inverse of 2 is 1/2, right? And in terms of the field of integers, there's no 1/2 in an integer set. So I can't go backwards there. Anyways, before we get too convoluted with that, let's talk about the GF2 field, because that particular field is part of your homework and your textbook stuff. So the field of GF2 is a set of numbers 0s and 1s, and I only have 0s and 1s to use for this field. So a field has an addition and a multiplication. It has to be well defined, and so what we can do is we can define an addition table and a multiplication table so that we can do the addition and multiplying. So when we add 0 and 0, that's obviously going to be 0, right? And when we add 0 and 1, that's just going to be 1. When we add 1 and 0, that's going to be 1. What happens when we add 1 and 1? We get 2, but 2 is not in our field. So let's bring that back to our field. What would make sense to put in here when we add 1 plus 1? 1 or 0? Yeah, that's what I meant. 1 or 0, which one? 0 would probably make more sense. Why? Because when you take the sum of 1 and 1 and you get 2 and you divide 2 by the base, this is base 2. That's not what I meant to say. What I meant to say is that when you divide 2 by the base, you have no remainder. Your remainder is 0. So this is all about remainders. And if you're a computer science person, you probably know this as the what? What? The what? Modulus. Module. So it's the mod function in computer science. So setting up your addition table gives you a modulus function. The multiplication is based on 0s and 1s again. So 0 times 0 is 0. 0 times anything is 0. Then we want to keep that rule. And then we have 1 times 1, which is 1. And so that's our simple multiplication table. Okay? So if I happen to have a vector let's say I have a vector in GF2, and I want, how many do I want? Let's just stay with 4 dimensions. So if I have a vector in GF2 that has 4 components, that would just be a bunch of zeros and ones in 4 different components. So 4 zeros and ones, let me just randomly make up a vector. And then if I have another vector, W, I can think about adding these vectors because I have this addition table now. So if I were to add them, let's do this carefully. I have 0 plus 1 in the first component. And here, since I'm adding, I'm going to put commas just to be clear. 1 plus 1, 1 plus 0, and 0 plus 0. And then all I have to do is look at my addition table to see what the results are. So this is just going to be a 1. 1 plus 1, that's the one that I kind of struggled answering Madhav's question. So, wait, that should be a 0. And then 1 plus 0 is 1, and 0 plus 0 is 0. So that's what you get when you add these 2 vectors in GF2. Yeah? Well, that's the other thing about this. First of all, it's 4-dimensional, so it's hard to... You're working in 3 dimensions. The thing about this is that you have what's called a finite vector space, and we're not looking at. This is one of those ones that are even in R3. It's going to be even in GF2 in a 3rd dimension. You're not going to be able to visualize this. So when we go back to this idea of a finite field, like this, when we only have 2 numbers, we're not going to be able to visualize it. The advantage we do have is that we can list all the vectors. So I can list all the vectors in GF2 to the 4th or GF2 to the 3rd. I can list them all, but I can't visualize them. There's no graphics to them. Can you list down all the vectors? I'll just pretend you nodded your head. Yeah.
So just clear GF function, right? Whether the remainder is equal to the base.
Yeah, if the remainder is equal to the base, actually if the remainder is a multiple of the base, it's going to go back to 0. And we'll make that clear with our next example where we have not the GF2 but something else. Okay? So in the book, I just call it GF2 because it sounds cool. In the book, they actually call it Z2. So this is an integers modulus 2. Okay? All right, so now for fun, let's make up a Z5. So let's make up a field called Z5, and let's put, well, we know that this Z5 is a finite field that only has 5 digits in it. And we also know that we all like starting with zeros. So let's go 0, 1, 2, 3, 4. And then I'd have to stop because I only have 5 numbers to deal with. So let's make an addition table. And a multiplication table. So if I add 0 with anything, I'm just in the first row and the first column is just going to be the original numbers again. Okay, so now let's add 1 plus 1 is 2. Is 2 in our set? Yep. 1 plus 2 is 3. That's in our set. 1 plus 3 is 4. That's in our set. 1 plus 4 is 5. Wait, that's not in our set anymore. What should it be? 0. Okay, 5 divided by the base, our base. 5 divided by 5 is 1, and your remainder, remember, that's what you're looking for, is 0. All right, 2. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5, so what should this be? And 2 plus 4 is 6. What should this be? 1. So that should be 1. And then same thing here. 3, 4, 0, 1, 2, 4, 0, 1, 2, 3. And if you finish this table, whether you do it on your own or copy it, you see the symmetry here. It's kind of interesting. It just kind of rotates around. And people tend to look at this in a circular form. I think that's how the book does it. So if you want to count to 15, for example, you would start from 0 and you say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if you happen to land on a 15 in your computations, mod 5, that's going to be 0. So you could do it that way if you want. You can also go backwards. 0, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. So positive would be, I guess the way I drew this is a clockwise direction. Okay. All right, multiplication table. We know that 0 times anything is going to be 0. So the first row and first column would be just a bunch of zeros. 1 times anything is itself. So now we get to the interesting parts. 2 times 2 is 4. Is 4 in my list? 4 is in my list. I can write 4 down. 2 times 3 is 6. So I can use my circle here now. 1 or 0, 1, 2, 3, 4, 5, 6. So this should be a 1. 2 times 4 is 8. I'll count again. 5, 6, 7, 8. So that's a 3. I landed on a 3 when I went on my circle. Okay. You guys want to fill in the rest? 3 times 2 is 6. 3 times 3 is 9. 9 mod 5 is 4. 3 times 4 is 12. Mod 5 is 2. So a quick way would be just to divide it and look at the remainder. 4 times 2 is 6, which is 1. 4 times 3 is 12, which is 2. 4 times 4 is 16, which is, should be a 3. Okay. All right. Look interesting? So now I can, again, add and scalar multiply these vectors, right? So let's make up a vector in Z5, and let's say this has dimension, should we keep it at 2? Nice and simple. Just a 2 vector. So an example of a vector there would be just a vector 2, 4, and then another vector. An example of this would be like 1, 0. Right? So I can add them. So what's V plus W? Well, it has to be a vector. 3, 4. Now that wasn't interesting. Oh, we can also scalar multiply. What's 3V? It would be what? 6, 12? I don't have 6 and 12s in my thing. So it should be 1 and what? 1 and 2. So it's not 6, 12, although you probably want to think 6, 12 to help you figure it out. But since you're in Z5, you need to stick with the numbers that are in Z5, which is 0, 1, 2, 3, and 4. Okay? All right. All right, so there are interesting applications that they have in the textbook that talk about these things. And I think I'll leave you to look through the problems and read it. And I want to try to jump ahead and define our new operation for addition, which is the dot product. We're here till 2, right? Okay. I get mixed up. Sometimes it's 1:55, or sometimes it's 2 o'clock, sometimes it's 2:05. I guess when I teach the calculus one, we end a little bit earlier. So the dot product is our first multiplication between 2 vectors. So we added vectors, we subtracted vectors, we scalar multiplied vectors, which is a scalar times a vector. But that's as far as we got. So now in terms of multiplication, we want to see how we can combine 2 vectors together. And this is our first way. Actually, in this class, this is our only way. If you've taken physics or Calc 3, you guys might have learned about the cross product. We won't talk about the cross product in this class. So right now, or our only multiplication of vectors that we're going to talk about is the dot product. So this is the dot product, and this is how it works out. You take 2 vectors, and then you're going to multiply each component, component by component, and then you're going to add them. When you do that, what is the significance in your result when you do a dot product? It is a scalar. You get 2 vectors, you combine them, and then you get a scalar. It becomes a scalar. So that's pretty significant. It's not like you multiply 2 vectors, you get another vector. That doesn't happen here. That happens in a cross product, which I said we're not going to talk about. But this one, this particular multiplication of 2 vectors results in a scalar. So that's why they sometimes call it a scalar product. And then they also sometimes call it the inner product. Because I don't know why. I'll tell you why later on. There's this thing called the outer product too, which is kind of cool. But we won't talk about that until we talk about matrices. So the scalar product is this operation, and so we should be able to do this with a bunch of examples. I mean, the algebra seems like it's pretty simple. I think that's the easiest part of this, is the algebra, is computing it. The more complicated parts are like the meaning of it, and maybe the computation in like Z5 or Z2. So let's do an example. And let's start off in R6. You remember how Maria did in this class? So let's do an example of a dot product in R6. This is Maria's grade vector. And if I remember correctly, which I probably don't, I can have a grade distribution for my class. I think my homework was 10%, or was it 15? What? 15%. The quizzes were also 15%. Really? I can look it up. 15, 15, 5. Oh, the worksheet's 5, the STEM speaker series, and then 35 and 25. Let's see if I remember that. 15, 15. This was the exams. Oh, I forgot already. 35. The final exam was 25. The STEM speaker series was 0.05. And the worksheets were 0.05. So homework, quizzes, exam, final, STEM speaker series, and worksheets. Okay, so I have Maria's grade, and I have my grade distribution vector. So for me to actually calculate her overall grade, I simply take the dot product. So MT dotted with my grade distribution is going to be the dot product of this. So 0.4 times 0.15, comma, wait, is it a comma? It's a plus, right? We're adding these things. So I'm not getting a new vector. I'm going to get a scalar out of this. So plus 80% times 15 plus 75% times 35 plus 100% times 25 plus 100% times 0.05 plus 0 times 0.05. Okay? So whatever she gets here would be her overall grade. She's computing it right now. So during the semester, don't ask me what you're getting, how you're doing in this class. You figure it out. You calculate your quizzes, You find the average of your quizzes, you find the average of your exam scores, and then figure it out yourself. It's a dot product. What do you get? What'd you get? Oh. Sorry. Okay? So that's a dot product. One more dot product. Let's say we had a vector in GF2, 5 vector in GF2. 1, 0, 5. So we could take the dot product again. We know how to multiply in GF2 and in any finite field now. V dot W, the dot product here, is going to be equal to what? So 1 times 0, 0, 0 times 0, 0, 1 times 1, 1, 0, 1, 0, 1, 1, that's 1. And then that's it, and that's our dot product. What? Yeah, good catch. So sometimes I make mistakes on purpose. And I just expect you to be able to catch it. So what's this equal to? 0. You could say 2, right? But just say it in your head. Don't say it out loud. And then mod 2 is going to be, it's going to take you back to 0. Okay? Yeah. Yeah, there's a lot of ways to do that. So sometimes people just say 2 mod 2 in the bottom, and then if you're handwriting it and stuff. In computer science, there's symbols to actually compute it, and we'll take a look at that also. Okay, so at least we got to the dot product. We're, again, a little behind. Next time we'll talk about lines and planes, and we'll go from there.